So here we go. I'm recording from now on. If you do speak up, then please know that speaking up, I'm probably going to be, or I will be posting these notes online. So if you speak up, your voice is going to be heard. I will try not to call out any specific person, just so that you guys can remain anonymous. So. As you start by taking a look at all of these graphs, if you notice on the notes, I do have links to GeoGebra. These two links on GeoGebra can be very helpful in terms of doing more manipulations of what the Inspire can do. If you notice over to the right, I have the Inspire showing up. With the Inspire showing up, what I did was on the graphing section, I went to menu and I did graph entry and I went into polar. Last night I talked about doing stuff with parametric. This time I'm going to be focusing on polar. So when it comes to polar, it defaults that you're going to go from 0 to pi. So you're going to be graphing one full revolution of it, which for most graphs, most of the big graphs that we do, 0 to 2 pi is enough. There are going to be some graphs that might require a little bit more, and if that's the case, then we can always change these values. So starting off, I do want to have the calculator do a lot of these, but really, I feel like one of the biggest benefits of working with polar is, just so you know, the theta step. The theta step, this is just a randomly generated theta step. You can make this as big as possible, or as small as possible, or sorry, as small as possible. But know that the smaller you make it, the longer it's going to take to actually draw out the graph when you kind of go through tracing. So, all right, back to this problem. One of the things that I like to do when it comes to any of my polar graphs, notice everything, it's really saying R is a function of theta. Now, really R is not necessarily a function of theta. When we start getting into like polar, we start getting into a lot of the other applications. Jimmy, one more time, if you go menu, sorry, I didn't mean to just call you out like that again. If you go to polar, or to menu, graph entry, go down to polar. And I apologize for mentioning your name. So when you start getting into working with parametric or polar, we stop losing the identity of what is considered like a dependent, independent variable. Really, all of the variables tend to be codependent on each other once you get to parametrics and polars. So I like that terminology as codependent. I'm probably going to be butchering some form of the actual definition of codependent, but I'm sorry for all the math geeks out there. So when I have R equals 3 plus 3 cosine of theta, what I typically like to do to graph this, let's go ahead and establish what theta is. Theta is, with cosine, I like to come up with values of cosine. They're very easy to graph. So when theta equals 0, cosine of 0 is 1, so this is really 3 plus 3, which at the angle 0. And the way we're generating this point, each point is actually listed as r comma theta. I prefer to put it in as theta comma r, because that way I look at theta as the independent variable, even though it's not exactly an independent variable. So when theta is 0, when that angle is 0, the radius is going to be 6. For cosine, I like to generate as many points as possible that are easy to actually graph. So cosine, all the pi over 3s for cosine, all of the pi over 3s give us a nice cosine value of 1/2. So this is going to be 3 plus 3/2, or 4.5. So at pi over 3, which is right here, I'm going to be going out 4.5. And then, of course, pi over 2. At pi over 2, we end up with 3 plus 0. At 2 pi over 3, it'll be 3 minus 3/2, which would be 1.5. And then at pi, we will have 3 minus 3, which would be 0. So for all of you out there, if we connect, and I really should connect from theta equaling 0 just so we can see how this is generated. what we can see is this is the top half of a lemmasome. Sorry, this is a cardioid, although a cardioid is a special case of a lemmasome. We can continue on and graph some more points if we want to do 4 pi over 3, et cetera, et cetera. But we know that if you remember from last year in pre-calculus, we know that if we have a 3 plus 3 cosine of theta that has symmetry with the polar axis, symmetry with the polar axis kind of translates to symmetry with the x-axis. And the reason why we know that is cosine of negative theta is equivalent to cosine of theta. So if we were generating negative angles, then those negative angles would be generating the exact same points. So we would have negative pi over 2, so rather than, sorry, negative pi over 3. If I want to generate the points this way, we would have the exact same values. And I think I graphed that point wrong. So let me go ahead and clean that up. So that should have been 4.5, not 3.5. And this should be 1.5, and then you get 0. There are mainly 3 or 4 different types of graphs that you're going to get. What the ones that the AP usually will focus on, which I know the AP is not going to be doing that for the 2020 year. The AP will focus on cardioids, lemmasomes, lemniscates, and circles. So what I wanted you guys to see with this problem was how to generate it. And any overall questions on how to generate this cardioid? So this is a cardioid. I'm not seeing any. I'm also, how picky am I going to be with point accuracy? That's a very good question. Well, the points that I truly am going to care about are going to be the points of intersection of multiple polar graphs and looking to see what's going on in that. As far as I like to have the, for cosine, all of my pi over 3s, mainly because pi over 3 tends to be a nice value. For the sines, I like to use the pi over 6s. It's not hard to mentally generate. I know Diamante always loved, and I probably shouldn't mention her name, but okay. Your teacher last year typically loved to see these T-charts. I don't necessarily need to see the T-charts because I assume that you guys are intelligent enough that you can start plugging in those values. For me, it's going to be, I will show some of those T-charts just because I want you to see, kind of like my mental thoughts, but I don't necessarily expect your mental thought written down. I expect to see these points. If you don't have them, like I know with my pre-calc kids, I try to have as much accuracy as possible, but I have a lot of kids who just end up doing something like that. In my mind, that is a travesty because it doesn't show just how wide that lemmasome ends up getting. Plus, it's also laziness. And I know there are certain students who like to have that laziness, but I'm not a lazy person. So, going on with this one, if we start with the points, again, the mental points that I'm going to go into are start off at 0. When theta is 0, I get a radius of 3 plus 0, which should be right here. Because this is sine, I'm going to be using a pi over 6. This will be 3 plus 1. So at pi over 6, I'm going to have a radius of 4. When I have pi over 2, I will have a radius of 3 plus 2, which is 5. If I have 5 pi over 6, once again, I have a radius of 3 plus 1. And what you should start seeing is you should see some symmetry along this. And then at pi, we're going to have a radius of 3 plus 0 again. That should be right here. As we went from 0 to pi, we should see this theta equals pi over 2 axis that has the symmetry. and that's because of sine. That's one of the key characteristics of a sine polar graph. So if we want to start treating these as negative angles, we can. In fact, that's really not a bad idea to look at these as negative angles. Actually, let's go ahead and continue this until we get to the 3 pi over 2. 7 pi over 6, this will be 3 minus 1, which is 2. And then if we go 3 pi over 2, we will have 3 minus 2, which is 1. And we can use symmetry, or we can actually work out the other points to get this graph. This is called a limacone without a loop. At least that's what we call it in pre-calculus. Or at least that's what we call it in the regular pre-calculus. I know that, or I'm actually not sure what your teacher last year actually, or how they phrased it, because your teacher last year dimpled limacone. Thank you to the student who said that. She said dimpled limacone. That's fair. There are a lot of different ways that you could describe all these different things from happening. Yes, I do expect you to know the general shape of these graphs. The general shape of these graphs, what kind of graph gets created. And the reason why I want you to know the general shape of these graphs has to do with when you start to graphing and you want to find, eventually, in the next section, we're going to find area enclosed between graphs. I expect you to be able to look at an equation and say, I know based on that equation, do I have symmetry to the polar axis? Do I have symmetry to the theta equals 5 over 2 axis? What kind of symmetry occurs and why? And a lot of that is going to be important because when you're finding that area, that enclosed area, if you look at radii as negative values, sometimes it's kind of like looking, let me kind of show this off to the side, kind of like looking at a sine graph and saying, okay, the sine graph going from 0 to 2 pi, the area of that sine graph is not 0, but the net change is 0 because this positive area ends up being opposite this area. When it comes to polar, it's not quite as obvious where you have a positive radius and where you have a negative radius. And because you don't have that as obviously, sometimes when you integrate, do all of your integral work, you end up getting a net value of 0. You're like, okay, well, I know the area is not going to be 0, so what happened and why? So by knowing the overall shapes of the graph, you can kind of get an idea of how those graphs are created, which is why I'm going through it right now. I want you to see how the graphs are created. A question that was asked, it does, it's just dimpled. It doesn't actually like curve in. I guess this one probably does curve in a little bit, hence the dimpled. So knowing how that graph's created tells you when you have a negative radius, because that negative radius is where you're going to start getting some areas that generate as 0 when you do your integrals. So we're going to have to do some creative manipulation with our integrals and area to make sure that we only have positive values. So big question will typically be asked, how would I know that this is a dimpled limacone versus one that has an actual loop? When I do, let me change colors really quickly. If you notice that the maximum value of the radius occurs at theta equals pi over 2, and that theta equals pi over 2 gives us a radius of 3 plus 2, and then the smallest radius occurs at 3 minus 2. The dimpled limacone ends up showing itself because the smallest radius is 1, the largest radius is 5. You will never have a negative radius. Since you never have a negative radius, there is no loop. So no negative radius equals no loop. The only way a loop is going to occur is when you end up with a negative radius, because in order to change from a positive radius to a negative radius, you have to go through 0. And that's not this problem. So this is a perfect opportunity to go to the Inspire. And I'm already on polar, so that's okay. So let me go ahead and generate this graph. This is 3 plus to your sine of theta. And theta should be under here. And I'm in degrees. I kind of had this in degrees from my pre-calc code, so let me change the settings really quick. I want radians. Okay, so that would be the graph that I have there. If I scroll up in the question, I don't like to look at it as A and B versus B and A. For some situations, I know that's important. But the only way that I can have a negative radius is, oh, I can do that. Give me just 1 second. If this number in front of the sign is bigger, now what you can see is I am going to have a loop. And that loop is occurring because, I'm going to go back to the equation. I should be able to come up with a pointer. Give me 1 second. Actually, I can do the point. Nope, can't do the pointer yet. I'll work on that. So if I take my radius as 3 plus 4, that's going to give me an overall radius of 7. So the largest value here is going to be 7. Now, going back to the equation, if I have the smallest radius is going to occur at 3 pi over 2, and that'll give me a radius of 3 minus 4. So that radius of 3 minus 4 is -1. So that radius of -1 is what creates the loop. And so as far as A and B goes, when B is bigger than A, we create a loop. When A is bigger than B, there is no loop. And it is a limmason, not son, but son, limmason, with a loop. Next question, R equals 2 cosine of 3 theta. So perfect opportunity. Let's go ahead, and these are a little harder to draw, which is why I want you to go ahead and use your Inspires. So tab, let me go ahead and do this. If we have 2 cos, that's just for you. 2 cos 3 theta, 2 cosine of 3 theta. It's like ln. 2 cosine of 3 theta. What you're seeing here is you're seeing what we call a rose. I don't like it either. So this is a rose. It's a rose with 3 petals. If you remember or don't remember, let's go ahead and play instead of changing this. In fact, I think we could probably create a slider. Yeah, let's create a slider for A. So if A equals 1, which is what's going on here, if A equals 1, then we're going to have a circle. So it's really a rose with 1 loop. When A, oops, okay, when A is 2, I had not, and there you go. When A is 2, we should have 4 loops. When A is 3, we have 3. When A is 4, we have 8. When A is 5, we have 5. Now, for those of you who are wondering why this is going on, tracing kind of will help us see exactly how this is created. So if we go into trace and let's plot the path in polar. So the first loop gets created. Now, if you notice, we're supposed to be working at the angle of like pi over, somewhere around pi over 6, somewhere between pi over 6 and pi over 4. We're working backward, and you can see right down here that the radius ends up being negative, even though this is r comma theta. The radius is negative, even though we're having a positive direction. So it's the negative radius as we continue tracing this around. You can see all 5 petals get created as we go from 0 to pi. And there really are 10 petals as I'm continuing all the way through 2 pi. So there are 10 petals, but whenever you have an odd number in front, that odd number will show that you're going to have 10 petals, but they're all retracing themselves. Or in this case, you're always going to have that number of petals because they're always retracing. It's when you have an even number, and let me go ahead and change this back to an even number. Sorry, that's my daughter in the background. So this is 4. Let's go ahead and redo the trace. And for the person who said remembering this is kind of tough, that's one of the reasons why at the beginning I kind of go through more of the pre-calc stuff, just so that we can bring it back to memory. For the person who said that, yes, my daughter loves math that much that she's that excited. So as you go and you start creating this, and I encourage you to be doing this on your calculator as well. If you notice, it's right here that we're at pi, and we've only created half the entire graph, and that's because this is an even number of petals, or this is an even coefficient in front of it. And so going all the way to 2 pi, we get all 8 petals. So now, in order to do this one, r squared equals 9 cosine of 2 theta, we can't really do this without actually doing some algebraic work. For the algebraic work, if we take the square root, we get positive or negative 3 square root of cosine of 2 theta. I'm not going to go in any more depth than that, but if I go ahead and in the calculator, let me get off that. Nothing like having too many screens open at once. So I'm just going to make my life easier. Let's doc B it and start again. Come on. Doc B. All right, go to a graph, menu. Let's get back into folder mode. And now if I do 3 times the square root, which, oops, not shift, control. So 3 times the square root of cosine of 2 theta. Let me go ahead and get theta on here. We get what's called the lemniscate. Let's go ahead and do what we did before. Let's trace that out so we can plot its path. That as you're going forward, you notice how the radius ends up being undefined during that portion. So I'm going to continue moving that on. Okay, I do see the question about doing example 3 by hand. I'll do that really quickly. Let me finish this one. We have an undefined radius because when you start talking about certain values of cosine obviously will give you the range of -1 to 1. By having that range of -1 to 1, sometimes you're going to have negative values that come out of cosine. And so as you're continuing on, what's happening is there actually is an imaginary loop that's being created right here. So when it comes to the lemniscates are a little bit fatter than a typical rose petal, but you have an imaginary petal that's being created down here. So when you look at a lemniscate, this would have 4 petals, but because we're not able to have negative answers that come out of this, the 2 petals that were negative radii, end up giving you only 2 petals that we can see. And let me go ahead and move this. I'm going to try to move this. And it's not letting me click on it. Okay, whatever. So if I graph the negative square root, because if you see right here, I only graph the positive square root. If we graph the negative square root, which I could do this as, I'm gonna check here, we should be able to say negative R1. And did that actually graph is the question. It's in red. It should be the exact same graph. There we go. I'm not seeing it on here, probably because it's overlaid. Let's turn that off. I'm not sure why that's not actually graphing it. Anyway, it's the exact same. So how would I ask you to graph this one by hand? I would ask you to notice that this is a cosine graph, and cosine does have the symmetry to the polar axis. And the largest radius is going to be, when r squared is 9, so the largest radius is 3. And really, at this point, rather than do all the deeper analysis, if I wanted you to, I would have you do it. But rather than do the deep analysis to say when 2 theta is going to give you the pi over 3s, so it's really pi over 6s. If this were a much more rigorous class, I would have you do that. And you guys are like, wait a second, this is rigorous enough already. But as I said, this ends up being slightly fatter. Typically, I just do it kind of like as an infinity sign. It's not ideal, but these are sort of hard to graph without plotting point by point. So going back to this one, how would I ask you to graph this one? Cosine of 3 theta, one of the things that I like to see is when does 3 theta actually equal, when does cosine of 3 theta equal 1 or negative 1? And that would be when 3 theta equals, let's start off with cosine of 3 theta equaling 1. So 3 theta equals 0. Now I'm going to throw 2 pi into here, and I'm going to throw 4 pi into here. Now, if you remember from pre-calculus, where if you have a 3 theta, that means you have to go 1 period, 2 period, 3 periods out. And so that way, when you divide by 3, at the theta values of 0, 2 pi over 3, and 4 pi over 3, that is where you're going to have radii of 1. So let me go out the angle of 2 pi over 3, which is along that path. You're going to have a radius of just 2. Just for the sake of, I'm going to change this up so we can see it a little bit clearer. Let's make this r equals 4 cosine of 3 theta. So now at the angle 2 pi over 3, we are going to have a radius of 4. Kind of skipped over at the angle of 0, we're going to have a radius of 4. And at the angle of 4 pi over 3, we're going to have a radius of 4. If I wanted to be a little bit more specific, also, I could say, when does cosine of 3 theta equal 1/2? Because those are nice values to graph. I could do the same process to say 3 theta is going to be at pi over 3. And then we would have 5 pi over 3 and 7 pi over 3, 9 pi over 3. That gets a lot more complicated in terms of plotting points. And I know your teacher from last year loved having you plot points, and while that's valid, at some point we need to say, okay, we know what the general shape is. If we want to know where they intersect, that's going to be important too, just not at the moment. So this is 3 petals that occurred here. When does cosine equal 0? That somebody asked that. That's an important thing too. We're going to see some of that. When does cosine of 3 theta equal 0? That would be 3 theta equals pi over 2. 3 pi over 2. We have to go out 3 full periods. So 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2. So that when we divide by 3, we're always going to have cosine equaling 0. And thank you to the person who asked that, by the way. Why this is going to be important is as we get into some of the calculus, trying to figure out where we have a radius of 0, where we have slopes of 0. all of that is going to come into play from knowing when theta equals, or cosine 3 theta equals 0. So that would be at pi over 6, pi over 2, 5 pi over 6, etc., 7 pi over 6, 9 pi over 6, which is 3 pi over 2, and then 11 pi over 6. As far as your graphing, because this is more of a calculus, and by the way, Slytherin 10 points. Because this is more of the calculus and less of the pre-calculus, we still need to know this pre-calculus work. Knowing how these graphs are generated is why I'm going through this. The generation of all of these graphs is extremely important because you need to know like when you end up with a radius of 0, when your radius ends up, or when you're at the tip of the petal. Like all those details, they come out in the problem, and you're sort of expected to know, hey, yes, I can figure out how to get there. So, the last bit, which is really not quite as essential in terms of the pre-calculus knowledge, it's essential more for as you're going. For the person who asked why the pedals go 4 instead of 2, what I did is I changed this to 4 just so that I could have larger problem, or like a larger pedal for me to be able to visualize. Otherwise, I would be graphing very tiny pedals like that, and that didn't really show a whole lot. So sorry for my son who's in the background having a good time. So, so converting between rectangular and polar, it's not 100% essential, but at the same time, it's useful, especially as you're about to go into multivariable calculus, where if you notice at the top, I said, hey, what are some of these relationships that we use? Basically, are the conversions between polar and rectangular are these 4 equations. X is r cosine of theta, which we're going to do a lot of work with here today. Y equals r sine of theta. But where we go conversion from rectangular to polar, we know that x squared plus y squared equals r squared. So I'm going to replace this x squared plus y squared with r squared. Now, x squared minus y squared is not quite so obvious. So I don't know what x squared minus y squared is. So what I'm going to do is I'm going to replace the x squared with r cosine theta. And then I'm going to replace y squared with r sine theta. And so, by the way, that's r squared squared. So I have r to the 4th minus 4. If I factor out the r squared, then I'm left with the expression cosine squared theta minus sine squared theta. And I don't know how many of you recognize that cosine squared minus sine squared is the double angle formula. So I have r to the 4th minus 4r squared cosine of 2 theta equals 0, which gives me r to the 4th equals 4r squared cosine 2 theta. And I hope you know where we're going with that. If we divide both sides by r squared, we now have r squared equals 4 cosine 2 theta. So what kind of graph is this? State the type of graph that results. R squared is 4 cosine of 2 theta. Because it's r squared, this is a lemniscate. All right. If I have r equals secant of theta times tangent of theta, now what can I do with this? If I know tangent of theta is y over x, so r equals secant of theta, which is 1 over cosine of theta. And tangent of theta is, I'm just going to leave this as tangent of theta right now. What I can do is I can multiply both sides by the cosine of theta to get r cosine of theta equals tangent of theta. And because I have r cosine of theta, that's equivalent to x. tangent of theta is y over x. So this is y equals x squared. So this is a parabola. Now, somebody did mention about r squared equaling 0. If r squared equals 0, how about, let me phrase it this way more. When it comes to a lot of the conversions between systems, understanding that we might have some domain issues is something we always have to keep in mind. Keeping that in mind, we know that we just have to play it problem by problem. There's not any good way of universally saying this is what's going on. So I did give you all of these different, just all these different shorthands. So if you have any questions about what they generally look like, this gives all of the basic rules. Remember, the whole point of everything I'm going to be asking you to do is going to be a little bit less of some of the specifics in terms of, yes, I want you to know where the tips of the pedals are. I want you to know where all the different intersection points are going to be. But we need to have a general idea of what these graphs are going to look like so we know what to do with it. And then we're going to be using the calculus to find exactly where all these different things are going to occur. For instance, if I have a rose curve, this is going to be important to me because that's where I'm going to have a slope of 0, as well as like that point, these 2 points as well. We get to analyze, like for today, our goal is to figure out a lot more of the derivative aspect of what's going on with polar graphs. For the next session, we're going to be talking more about like the integral aspect, which is why areas are going to be coming into play, because that's where integrals kick in. So, slope in polar form. Now, as we learned when it comes to the parametrics, we could take this parametric and say the slope is dy dx, the slope of dy dx, where in parametrics we called this dy dt and dx dt. We're now going to refer to them as dy d theta and dx d theta. And for the person who asked about, yes, I'm going to be more concerned about analyzing what's going on, and that's where the calculus side is going to kick in. So dy d theta, we have as dr d theta sine theta plus r cosine of theta. So we have two different things we can do. We can either say, hey, let's memorize this, or we can derive it. Since I'm not one that says I like to memorize things, let's go and actually derive what's happening. So let's go back into what is dy d theta. Dy d theta, we start off with y equals r sine of theta. And if you remember from, oops, that was not supposed to happen. My apologies. So if y equals r sine of theta, if you remember back in chapter 2 when we talked about implicit differentiation, we are now going to find dy d theta. And there is a product rule that's occurring. Thank you for the person who said that. There's a product rule that's occurring where we will take the first times the derivative of the second. Let's actually do it in the way that I normally do it, which is I usually say the derivative of the first times the second. So b du minus u dv. The derivative of r is dr d theta times, let's say u v. So this is going to be v du. Dr d theta times sine theta plus, that's where the u dv comes in. So the r times the du, which derivative of sine theta is sine theta. So this really is a straightforward product rule for y equals r sine theta. Similarly, if y equals, not y, if x equals r cosine theta, that's going to give us dx d theta is, once again, dr d theta times v, which is cosine theta, and then plus r. And I say plus, it's going to be r times negative sine of theta, which is why this is a minus down here. So for example number 2, one of the big notes that we need to make, if both dy d theta and dx d theta are simultaneously 0, we can't say anything about what's going on with the tangent line because of the 0 over 0. We'd have to do some more work in terms of L'Hopital's rule, but that's going to go into a lot more analysis and the nature of this course. Yeah, the hospital rule. All right, so if I have r equals 2 plus 2 cosine of theta, this is where all your questions about, what detail do I need to see? Let's start off by making a quick sketch so we can generically see what this is looking like. So when theta equals 0, I'm going to have 2 plus 2, which is 4. Now, first of all, I do like to say the fact this is 2 plus 2 cosine of theta means this is going to be a cardioid. So 2 plus 2 is 4. At theta equals pi over 2, we're going to have 2 plus 0. And we'll have 2 plus 1 at the pi over 3, 2 minus 1 at the 2 pi over 3. And this kind of looks like the cardioid that we developed earlier, correct? When a equals b, it is a cardioid. That's correct. And that's, so a cardioid is a special case of a limosome, where the limosome, you start going into negative radii, which is why you have the loop. Or if A is going to be bigger than B, we never end up with a negative radii, which is why it's a dimpled limosome. So here's our quick sketch. And the reason why I'd like to see a quick sketch of this ends up becoming, I want to know what's going to occur based on the question that I'm asked. For instance, find the slope of the tangent line at theta equals pi over 6. Let me go ahead and blow this up so we can see it a little bit better. I was zoomed in a little too far. So at theta equals pi over 6, I'm looking at what would the slope right here be? So to find the slope of the tangent line at theta equals pi over 6, we could either recreate, and honestly, when I was first doing the polar work, I would always re-derive this over and over again until I became familiar with it. I strongly encourage that over just the blanket memorization. But let's start off with, at theta equals pi over 6, what is our radius? Let me not do that color. Let's do something a little bit bolder. So if x equals r cosine of theta and y equals r sine of theta, we know that x is going to be at pi over 6. X is going to be r, which is 2 plus 2 cosine of theta, times, actually, you know what? I'm doing more than I need to. I was kind of thinking this as, I was pausing there for a moment. I'm doing more than I need to because this is really if I want to find the equation of the tangent line, not just the slope. We could do that if we want, but we're already running at this point. We're supposed to be done with it, almost done. Let's just go ahead and finish these notes, and then we could do more if we want to. So to find the slope of the tangent line, I do need to know what is r of pi over 6. Let's just go simple here. R of pi over 6 is 2 plus 2 times the cosine of pi over 6. So that'd be 1/2. So my radius is 3. And now, again, I encourage deriving it over and over again, but at this point, let's go ahead and start filling this in. What can I fill in? I can fill in the sine of theta. What is the sine of theta?
Isn't cosine of pi over 6 root 3 over 2?
Actually, you're right.
Yeah.
Okay, there we go.
Thank you for that correction. the reason part of my distraction comes down into, I realize there is something else we need to do. What is dr d theta? What is dr d theta?
-2 sine theta.
It is -2 sine of theta, right? So dr d theta at theta equals pi/6 is going to be -2 times the sine of pi/6. And hopefully I have this one right. The sine of pi/6 is 1/2. So dr d theta is -1. And now let me go ahead and rewrite this. Our slope is going to be dr d theta, which is -1, times the sine of theta. The sine of theta is going to be, the sine of pi/6 is 1/2. Plus the radius, which is 2 plus the square root of 3, times the cosine of pi/6, and the cosine of pi/6 is the square root of 3/2. All over, once again, dr d theta, -1, this time times the cosine, so square root of 3/2. And then don't forget that minus. And the radius one more time is 2 plus the square root of 3. And then times the sine of pi/6 is 1/2. So to clean it up, that would be -1/2 plus the square root of 3 plus 3/2 over negative square root of 3/2 minus 1 minus the square root of 3/2, which is a little bit cleaner. This is 1 plus the square root of 3 over -1 minus the square root of 3, or very nicely, -1. Isn't that beautiful? All of that work, and it comes down to a beautiful -1. And I know you could tell from your comments that it is beautiful, and I love that you agree with me on that one. So now what I was starting to get into is that if I want to find the equation, so my slope is -1, if I want to find the equation of that tangent line right there, I would go back into saying, okay, if x equals r cosine of theta, I could find the radius at that point, and then I know my theta value, so I can get my x value, I can get my y value, and I can find the equation of the tangent line in Cartesian coordinates. So part B is done. Give me one quick second. I need to take a drink of water. So give me one quick second. Okay. All right, I am back. So part 3, find the points at which the tangent line is vertical or horizontal. One of the reasons why I like to have a quick sketch of what's going on is so that I could say, where can I expect, and by the way, if you notice, the work we just did is right here. The fact that it's a slope of -1 sort of makes sense to me. So if I have a horizontal tangent, that's going to occur either here or here. If I have a vertical tangent, that's going to occur here, here, or here. So let's start off with, if I have a vertical tangent. So for the vertical tangent, So the vertical tangent is where dy dx is undefined. And that's typically where my denominator is undefined. So if we look and see back at our equation, it's where our denominator is undefined or our vertical tangent occurs when dx d theta equals 0. So where dx d theta equals 0. So let's go ahead and go back into what I had started with before. Probably should have just done it right from the beginning. Dx d theta, I guess this is just a rederiving. So dx d theta is dr d theta cosine theta minus dr d theta cosine theta minus r sine theta equaling 0. So where do I go from here? What is dr d theta? We found that right here. Dr d theta is 2 sine theta. You guys actually can't see that. Let me go ahead and highlight it. Here's my dr d theta. Try that one more time. So dx d theta is when -2 sine theta cosine theta, because that's my dr d theta times cosine of theta, minus the radius, which is 2 plus 2 cosine theta times cosine theta. Simplified is, does anybody recognize what this is? I see that as being 2 sine theta, but that's not going to help us at this point. So, good, bless you. So I want to know where this equals 0. Just trying to think of a faster way to simplify it. And
Wait, hey, Mr. Beck.
yeah,
When you rewrote -r times sine theta, you put a cosine theta in the second one. It needs to be 2 plus 2 cosine theta times sine theta.
yeah, so this would be the dr d theta cosine
Right.
theta
The next
minus r, oops, thank you.
sine theta.
Okay. Many thanks.
And then you should be able to factor it, right?
Yeah, so I knew something nice wasn't coming out of this. So because something nice wasn't coming out, I knew something was going on. My daughter just handed me a book and was like, read this to me. And I'm like, no. All right, so anyway. To simplify, let me just go ahead and multiply it out. I'm not distracted at all. So this would be -2 sine theta and then -2 sine theta cosine theta. So this would be, I want to know when dx d theta equals 0. This would be -4 sine theta cosine theta minus 2 sine theta. And for the person who is saying, hey, let's factor, for the people, that's 2 cosine theta plus 1. So basically, where sine of theta equals 0 and where cosine of theta equals -1/2 is where we're going to have our vertical tangents. I'm going to go ahead and shift this over just because that's where I started it. So sine of theta equals 0 at 0 and pi. Cosine of theta is -1/2 at 2 pi over 3 and 4 pi over 3. Definitely much nicer. So just to kind of confirm with what I did up here, you have my vertical tangents. Let me match it up with some shading. That was 0 right there. Change colors. 2 pi over 3 is where that vertical tangent occurred. And 4 pi over 3 is where that tangent occurred. Now, I did see somebody in the chat mention, well, what's happening at pi? At pi, if you notice, there is an issue. At pi, because this is a cardioid, at pi, we're going to have a sharp turn right there. That sharp turn is going to cause a lot of issues to happen. There is no vertical tangent there because it's an undefined point. Somebody asked, will you have to include 2 pi as well? That 2 pi, you could say 2 pi, but if you notice in the directions up here, 2 pi would not be included, so no, you don't. So all of that work just to find my vertical tangents. So what about the horizontal tangents? I should end up with 2 answers as horizontal tangents. Let me do this one in blue. So for me to have
Can we
the
just say that
horizontal,
pi is undefined?
say that one more time.
Do we just say that pi is undefined tangentially?
We are going to explain why in just a second. So it comes back to what happens if dy d theta and dx d theta are simultaneously 0. We can't really conclude. When somebody mentioned sharp turn, or having a cusp here, there is a sharp turn in terms of Cartesian coordinates, but it's not really a sharp turn. So like if you graph it as a Cartesian, it's sharp, but if you graph it in polar, it's not exactly sharp, which is why when we start talking about what's the equation of like all the tangent lines, when we have tangent lines, we do put everything back into the Cartesian, just so that we have that same frame of reference. So if you say sharp turn, that's okay. We can't even say the slope from the left isn't the same thing as the slope from the right anymore, because there is no left and right when we're talking about polar. So
Can we say like the slope approaching from the approaching from positive and approaching from negative is different?
that's a very good
Like
question.
the sides. Like
I
you know,
would-
like when it's like the superscript, like
Go ahead.
like superscript like left and right, like we're saying like a limit just from like the right, it's like 0 to the positive.
Yeah.
And so like we can say that because the slopes aren't the same from the right and the left, but like from the positive and negative side. Isn't that like the same?
You could. That would definitely be one way to do it. So let me say what I'm going to expect that you do. I expect that you look at and say, okay, I know that something strange is happening at theta equals pi. What's strange is happening is there is no horizontal tangent, there is no vertical tangent. There is a sharp turn in Cartesian, but there is a sharp turn in Cartesian. I don't have a great answer for that. It just comes down to how, like, what is it we're looking for? Does that make sense? Okay. So horizontal tangents. So the horizontal tangent is where dy d theta equals 0. And that dy d theta is what I still have highlighted up here. So that is dr d theta sine theta. So -2 sine theta times sine theta plus r, which is 2 plus 2 cosine theta. And I realize I'm working in the next space, and I'm sorry. That's okay, the next space doesn't need quite as much room. Times cosine theta. We want to know where that equals 0. So -2 sine squared theta plus 2 cosine theta plus 2 cosine squared theta equals 0. And this is where I'm going to, let's divide everything by 2, and I'm going to rearrange. I'm going to have cosine, let's show we're dividing by 2. So we'll have cosine squared minus sine squared plus cosine theta equals 0. So this is where knowing that double angle is going to be very, very important. Although it just occurred to me, you know, maybe I don't want to use that double angle. Let's put all of this in terms of cosine. So 2 cosine squared theta minus 1. And this looks like a quadratic to me if I do a rearranging. 2 cosine squared theta plus cosine theta minus 1 equals 0. So 2 cosine theta plus 1 minus 1. So it's where cosine of theta is 1/2 and where cosine of theta is -1. And cosine of theta is 1/2 at pi over 3 and 5 pi over 3. Cosine of theta is -1 at theta equals pi. And going back into highlighting, pi over 3 is where that one occurred. And let's do this as a lime green, 5 pi over 3 is where that one occurred. Now, once again, going back to that question of what's going on at theta equals pi, because theta equals pi occurs for both horizontal and vertical, it's inconclusive at that point. So there is no vertical or horizontal tangent at that point. And that's really the best way that we can explain it. So, last thing, all tangents to the pole. To find all tangents to the pole, we want to know, and let me kind of scroll back up here. If f of theta equals 0, so if f of theta equals 0 and f prime of theta is not 0, then the line theta equals a is a tangent to the pole. So I need to first understand where my, let me change colors so we can see difference. So first of all, where does f of theta, meaning where does my radius equal 0? And since my radius is 2 plus 2 cosine of theta equaling 0, this gives me where cosine of theta is -1, so theta is pi. So that kind of makes sense that we do have a tangent to the pole at that angle. We have to say, what is s double prime? It's not 0. It's actually undefined at that point. What that tells us is theta equals pi is the tangent to the pole. Can I define what the pole is? The pole is where the pole is, in essence, the origin. When you start looking at everything from a polar perspective, it's when your radius is 0. That's really the cleanest way of saying it. But the important thing is to say we know the derivative is not 0 as well. I hope this helps all of you. I'm going to go ahead and turn off the record, just so that if there are any questions you guys can ask, but the main notes are done.